Welcome to Lesson 11. So we're going to talk about the general chi-square test, which is a test that we use when we have two-way tables. So we're looking at categorical variables, two categorical variables. So two-way tables, we looked a little at them last week. Definitely make interesting proportion problems. So when we have two sample Z procedures, that allows us to look at a proportion. So when we break in a categorical variable into two categories among two groups. But now we can look at more than two categories from more than two groups. So that's essentially what we're going to get at. So we might want to compare, proportions for, 3 or 4 groups, or we might want to look at, the distribution of, 4 different categories across 3 different groups, that kind of idea. And we can use a general chi-square test and two-way tables to look at these. So the example that we're going to really focus on in Lesson 11 is the wine music example. So we have market researchers who apparently have total free reign at this particular supermarket. And they're looking at, apparently they stock Italian wine, French wine, and other wine, which, I don't know. I'm from Napa way back in the day, so that's what I tend to think of. Who knows? But Oregon's also pretty famous, I think. Not Napa famous, but... So we have a study that wants to look at 3 different treatments. They want to know if the type of music playing in the supermarket impacts the wine that's bought. So they go ahead and they randomly select certain days and they play French music. They randomly select different days and they play Italian music. And then they randomly select other days and no music is played on those days. And so on those various days, they go ahead and they record, well, how many bottles of French wine were sold, how many bottles of Italian wine, how many bottles of other wine. And they just want to look at them and see if, hey, does the type of music playing, does it have any sort of impact? Is it changing up sales? So we have a two-way table here. It's two-way because we have a categorical variable on one side, so music played. So music. So either no music, French music, or Italian music. And then we have wines sold. So bottles of wine sold here. And so two different categorical variables there. And so what we can do is fill in the totals for this table here. Right? So 30 plus 39 plus 30, you're going to have 99 individuals total bought. There were 99 bottles of French wine sold. If you're looking here, it's 31, right? 20 plus 21. So 31 bottles of Italian wine were sold. And then looking here, so 113. So 113 bottles of other wine were sold during this period. If I add it up, it should add up to, I think, 243. But we have another way to double check it by adding the other totals. So looking here, I have 75. Sorry, I'm just doing really quick mental math here. So absolutely it's worth double checking, and 84, 84. When I add those together, 84 plus 75 plus 84, I should get back to 243. Something's gone a little goofy if the total column doesn't add to the same number the total row adds to. So there were 84 bottles of wine sold on days that music wasn't playing. There were 75 bottles of wine sold when French music was playing, and there was 84 bottles of wine sold when Italian music was playing. So now we want to know, hey, do we have evidence that the type of music playing impacts the types of wine sold? Because if it has no impact, then roughly the same proportion of like Italian, French, and and other wine will be sold no matter what kind of music is playing, right? So if French wine is like half the sales, we'd expect half of them, no matter what music is playing, to be French. Of course, I'm making up that half number. So we can calculate the conditional distributions in proportion, so we can look at the type of wine sold by each type of music. We can also flip that around, but we're definitely interested in to see, hey, is there an impact by type of music? And definitely pull up a side-by-side bar chart. This is a nice way to visualize, hey, is the distribution different for each type of music, or does it stay the same? Because if it stays the same, then it doesn't seem like music had an impact. But if the distribution of wines sold is totally different for each type of music played, that the music probably had an impact. So we're going to compare the distributions of the wine purchases under the 3 music types, and to see whether or not they're the same as each other, or if they're different. And if so, an association may exist. Wording wise, an association existing means, hey, wine sales were impacted by music being played. And specifically, since they set this up as a randomized experiment, they could say that the music played caused this difference. So here are our 2-way tables. So this first one, if you're focusing specifically on music type, so there were 84 bottles of wine sold when no music was playing. 30 of them were French wine. So 30 over 84, which is roughly 0.357 of the bottles sold when there was no music playing were French wine. And then you can do that for all three wines. So you can do that for French wine, you can do for Italian wine and other wine, and then repeat for French music. There were 75 bottles of wine sold when French music was playing. 39 of them were French wine. Only one was Italian wine. There was something going on here. Very, very little Italian wine sold in that scenario. So here we have fractions. So these are exact, although sometimes it's helpful to switch over to decimals. It gives us a more meaningful, like, oh, what percentage is that versus a fraction. A fraction can be exact, but it's harder for us to conceptualize like what proportion that really is sometimes. So once again, this is a conditional distribution. We're focusing on type of wine sold. There is the other conditional distribution you could have focused on. Sorry, not type of wine sold, but type of music playing. You could have focused on type of wine sold. So here is our side-by-side bar chart. It would have been nice to have a little more space here. So green bars are French wine, orange bars are Italian, and yellow is other. So in the scenario of no music, you can see that 35.7% of the bottles sold when no music was playing was French, 13.1% was Italian, 51.2% was other. And then if you look at when French music's playing, it looks like French wine sales went up. It looks like Italian wine sales went down, and the other wine sales went down just a little bit. Then if you look at when Italian music's playing, it's pretty much, if you're looking versus French, it's lower percentage of a French wine was sold when Italian music is playing, a lot higher of Italian wine. So it looks like playing Italian music increased definitely. Like there were more people buying Italian wine when Italian music was playing. And then a little bit lower for other. So when we ask to compare, we want to know that do these 3 look like these 3 and these 3? Or are any sets of those 3 different from each other, and why? And so it looks like, in general, they always had more French and Italian, more French and other selling than Italian. But when you look at, especially when French music's playing, very, very little Italian was sold. Versus when Italian was playing, a lot more was sold then. So just worth commenting on. If we were asking to describe it, that was what we would be getting at, is how it changes when you look from group to group. Now those distributions, they would all look shaped the same if music had no impact whatsoever. But that does not appear to be the case. At least just visually it doesn't. So from the graph, which wine sold seems to be most strongly affected, I would argue Italian. When French music is playing, almost no Italian wine is sold. And then when Italian music's playing, the sales for Italian wines go up a lot. So I would argue Italian wines definitely seem to be affected by the music being played. So two-way tables. Still on our wine and music example, we want to note, is there evidence of an association between the type of music playing and the type of wine sold? So we want to just kind of use a combination of the table and the side-by-side bar chart. So looking here, the type of wine that customers buy, it seems to be considerably affected based on the music that's playing. So Italian sales are really, really low when French music's playing, but are higher when Italian music is playing. It's still higher than French music when no music is playing, but definitely it seems like when you play French music, fewer people are buying Italian wine. And then French wine, it seems pretty popular in this market. Pretty much no matter what music is or isn't playing. It's definitely probably better when French music's playing, but either way, and then if you look at the percent of the wines being sold that is in the other category, so it's not Italian or French, those wines, the percentage sold being other wines is fairly consistent. It's fairly close. It doesn't fluctuate as much as the other two types of wine. So our general chi-square test is going to be extremely similar in some ways to the best fit chi-square test that we just did in lesson 10. We're going to still want to have a random sample. We want our sample to represent the population as well as possible. And you're going to want to have two separate categorical variables that each have at least two outcomes. In reality, if they don't have, if at least one of them doesn't have at least like three or more, chances are you're going to probably use just like a two-sample z-test for a difference in proportions. So typically we want to have, tables that are at least, three categories in one of the variables. So we're going to compare the distributions in side-by-side bar charts to investigate this association. If there is an association, this implies that, hey, the category of one variable seems to be related to categories of the other variable. And so our goal, we're going to use this word association. We want to test see if there's an association between the two categorical variables. If there's no association, it's saying, hey, variable 1 and variable 2 aren't really related to each other. We can't find anything that says so. If there is an association, it's saying, yes, we find that there is a relationship between these two. So for the null and alternative hypotheses, these will be different. We will not write parameters in them. So the null will be there is no relationship or association between the two categorical variables. In context, you're going to want to say what those are. So if we are dealing with the music and wine example, we would say there's no relationship between type of music played and the type of wine sold at the supermarket. And then our alternative, there is. So by default, we assume nothing interesting is happening. There is no relationship. Our alternative, there is a relationship. There is something happening. There is something interesting going on. So expected counts, they're a tiny bit more steps than before. So if you want to calculate your expected counts, so you'll have an expected count for each cell in your table. It'll be your row total times your column total divided by your table total. So the total over all of them. So in the French, sorry, not just the French, the wine and music example, there are 243 people or bottles total sold. So 243 is our table total. So we'll show some examples setting this up. So for French wine and no music, my row total, so 99 times 84 divided by 243. So my expected value there is 34.22. It's okay that these are decimals. These are, expected values. They're average, like in the long run, this is what we'd expect. So if I wanted here, I need 99 times 75 divided by 243. We will have this filled in after. I don't know off the top of my head here. If I wanted here, 99 times 84 divided by 243. And you could do this for all 9 cells here. So 31 times 84 divided by 243. 31 times 75 by 243. And so on. You can do this for all 9 of them. And so that's one thing that's handy about me not doing this live, is that pause button. Because I don't necessarily expect y'all to fill these out as quickly as I'm talking, for certain. It's definitely a great place to press pause. I definitely recommend trying to calculate them on your own, and then seeing our filled-in table. Definitely give it a try. Doing stats is a lot better way to learn stats than watching stats. So the expected value for French wine when there's no music playing is 34.22 bottles. Which, granted, I mean, it's an average, so that's fine. So filling this all out. So here's the table all filled out. I promise we'd give it to you. So these are the expected number of bottles of wine sold if music had no influence whatsoever. So things that are nifty is if I were to add down, I would still get to 84. If I were to add across, I should still get to 99. Roughly. There are some rounding issues here. It's not perfect. But yeah, so, but without any rounding at all, when we add, you should get back to 99. You should get back to 84. All the row totals and the column totals still apply. So now conditions. It is important because any hypothesis test we do has conditions. Typically the very first one on any list is that we have a random sample, because we don't want to be doing these things for things that aren't. If we don't have a random sample, we usually have like an asterisk at the end saying, hey, this may not apply to the whole population, but we still usually continue, but just keep in mind. So things that are important, it's a little bit different. Our conditions here is no more than 20% of the expected counts are less than 5. So what that means is if I look at my expected counts, so if I look at this table, I don't want any more than 20% of them to be less than 5. And if you look, none of those are less than 5, so that's okay. But in reality, we could have like one of them be 5 or less, and it wouldn't be a big deal. But if we had 2 or more, that would be a problem. It would mean that we didn't get big enough sample sizes. So if the table's only 2 by 2, so you have 2 categories with 2 categorical variables with 2 categories each, all of your counts need to be at least 5. It's really, really important. Otherwise, you have just absolutely had too small of a sample size. It's going to be a problem. So all of your expected counts, they need to be at least 1, right? So we have this condition that, hey, this many of them could be less than 5. They all have to be at least 1, because if you're in a scenario where you don't even expect to see one whole observation in a category, you did not get a big enough sample size. So you need a much bigger sample size. So all of the counts need to be at least 1. And if you have some that are, higher than 1 but less than 5, that's okay, as long as no more than 20% of the cells have expected counts in that range. So just a thing to reference here, super old school. When I talk about a 2 by 2 table, 2 rows, so rows by 2 columns. So columns go up and down. Oops, well. I've never ever tried RC Cola, but I had a teacher that pointed out RC Cola. That's how we remember. Anytime I say, oh, if I have a 4 by 3 table, that means there are 4 rows and 3 columns. So that's how we talk about it in math and stats. Whatever number we say first is associated with the number of rows. Whatever number we say second is the number of columns. So just an easy way for me to remember is that RC Cola. You say your rows first and then your columns. So here, I think that pink part's off a little bit. This is going to look extremely familiar. This should look very similar to what we saw in Lesson 10. The observed count minus what we expected, square that, divide by the expected count, and then add all of those up. So however many cells are in your table, that's how many you're going to add together. The degrees of freedom, so that's going to be your number of rows minus 1 times number of columns minus 1. So it's going to be a little more complicated than it was before when it was just number of categories minus 1. It's going to be number of rows minus 1 times number of columns minus 1. Except for me even, well, I'll pull up the table and I'll show you what I want. So steps for performing the chi-square test, they're going to be extremely similar to doing the goodness of fit test. So we're going to state our null and alternative hypothesis. It will be a little bit different. We're going to say, oh, there's no association between variable 1 and variable 2, but tell us what those are, those variables, versus there is an association. Step 2, we're going to do preliminary analysis. We're going to look at the conditional distribution, so we're going to look at tables of the conditional distributions. Then we're going to look at side-by-side bar charts. Bar charts, side-by-side bar charts are usually the most useful visual tool we have for this one. Then we're going to calculate the expected counts, given that the null is true, and we really shouldn't expect different distributions for different rows or different columns, then we are going to perform our significant test. So we have to calculate our chi-square statistic. It's going to be extremely similar steps. I'm going to break it down extremely similarly. We're going to have our degrees of freedom. So this is going to tell us, hey, once we have our chi-square statistic, we need to take a chi-square table and look at a chi-square distribution with these degrees of freedom. So number of rows times minus 1 times number of columns minus 1. And then so get a p-value from that, or you can use TI-84 to get it. Step 5, I mean, really we're going to state our p-value and test statistic with our degrees of freedom, and then we're just going to wrap it all up. We're going to say, hey, this is what we saw in the bar plot, and hey, we reject or don't reject, and translation, what does that mean? So back to our wine and music example. So we're going to start off assuming nothing interesting is happening. That's what the null does. The null is dull. It really is. It assumes nothing interesting is happening. So we're going to assume there's no relationship between wine purchases in this store when no music, French music, or Italian music is played. So we're going to assume that the types of wine purchased do not have any association with the type of music playing. And it's specific to those 3, French music, Italian music, and no music. Goodness knows there's a lot of other music out there. Our alternative, so there is no. The alternative is saying there is a relationship between that. So we do think that wine purchases are related to the type of music being played, either no music, French music, or Italian music. So looking here, our preliminary analysis, so we kind of did this earlier where we're looking, and it really does. It looks like, when you go from no music to French music, it looks like French wine sells a lot more. Definitely a lot more than even in Italian music when French music's played. So French wine is sold the most when French music's played. Italian music is sold the least when French music's played, and the most when Italian music's played. If you look at other, it stays not super close, but 51%, 46.7%, 41.7%. It doesn't fluctuate nearly as much as the other 2 types of wine. The other types of wine, they fluctuate a bit more. So calculate the expected counts here. So here's what we observed. Here's what was expected. So we went ahead and did the, row total times column total divided by the total for all of that to get here. I personally find it useful to break it up in, let me see, well, one more slide from there. So checking our conditions, looking here, they're all higher than 1, right? All the expected counts are higher than 1, and technically they're all greater than 5, right? So I don't even have to worry about fewer than 20% of them are at least 5, or less than 5. They're all greater than 5, right? There's this one, it's less than 10, but it's still higher than 5, so we're happy. So the condition of the expected counts, yes, I would say we're well met. All of them are higher than 5. We're good. We're good to go. Not only are they all higher than 5, this is a 3x3 table, right? We have 3 columns and 3 rows, so we're definitely okay. So relabeling, for me, it's easier to look at it this way. So I'm going to say, okay, this is A, B, C, D, E, F, G, H, I. So this labeling is just because I want to make this into one long table, like we did with the M&Ms. So I'm going to make this one the first column, second, third, fourth, fifth, and so on. So I'll show you what I mean. So this is A, B, C, D, E, F, G, H, I. So that's where my labels are going. Yes, these are not the best labels here. French wine, no music. French wine, French music. French wine, Italian music. Italian wine, no music. Italian wine, French music. Italian wine, Italian music. Other wine, no music. And so on. Honestly, it doesn't matter what order you really put them in. I just find it easier to keep them in that order. So here's what was observed in all of them. So this is me making it a long table instead of having a table of observed and a table of expected and a table of observed minus expected. It's a lot easier for me to make this into one long table. Absolutely, you're welcome to make 5 separate tables of 3x3 tables if you want. So here are our expected. We calculated already. Throwing in our observed minus expected. So I'm just taking those first 2 rows and taking the difference. The order of the subtraction matters. You're going to do the observed minus the expected, not the other way around, although it's not going to have a huge impact on your answer after you square. Things to note, if I add it all the way across here, it will add to 0. Go ahead and square all of those. Now I have all positive numbers. Definitely feel welcome to press pause and double check. I strongly support calculating these first and then checking your answers. Doing stats is more useful than watching it. And then observed minus expected squared over expected. So there we go. If we add these all together, we get our chi-squared test statistic. Just looking here, like French wine, no music contributed 0.52 to the chi-squared test statistic versus French wine, French music contributed 2.337. So definitely that contributed more than the first one. If you look, these two, Italian wine, French music, and Italian wine, Italian music, those ones are definitely different than what was expected. If you look at what we actually observed versus what we expected for those particular combos, those two contributed a lot to this chi-squared test statistic. Those are ones that are really different from what we expected them to be. So yeah, there should be nine columns here, the way I have it set up, because we have 9 cells in our table, 9 combos. So now perform our test here. So okay, so you so if you add this all together, you get a chi-squared test statistic of what, 18.28, something like that. So if you look, definitely Italian wine, French music, and Italian wine, Italian music, those contributed the most to this test statistic by far. Which isn't too surprising. We definitely thought something funny was happening with Italian wine. So looking here, here's a chi-squared table. So we need to start with finding our degrees of freedom because it'll tell us which row to use. So number of rows minus 1 and number of columns minus 1. It's a 3x3 table, right? So it ends up being 4 degrees of freedom. 2 times 2 is 4. So now we're going to go to the 4 degree freedom row. And we're going to try to find where our test statistic of 18.28 is. So it's definitely not here. It's definitely not here. It is between these two numbers, right? So if you look up, that means our p-value is between these two values. So make sure you put the smaller one on the left and the bigger one on the right. Our p-value is between 0.001 and 0.002. Either way, it's pretty small. It's pretty small. It's less than 2 out of 1,000. So here we have so less than. You could even say it's between the two, but knowing that it's less than 0.002 tells me it's small enough that we're going to reject. So at the, I believe, was it 0.05? If we didn't state what significance level it is, 0.05 is a good default. If we did, use that one. Off the top of my head, I do not recall stating one, and we are going to reject. And then here, this is where we use that spectrum again. So if our p-value is smaller than 0.002, that's really small. That's really strong evidence. So we have very strong evidence to conclude that there's a difference in the distributions of wine purchases, Italian wine, French wine, or other wine at the store when no music, French accordion music, I didn't know it was French accordion music, or Italian string music is played. Yeah, I don't think we have those details about the instruments. Basically, given these three music options, the music playing seems to have an impact on what type of wine is being sold. French wine, Italian wine, or other wine. So here's some info on going ahead and entering this into a TI-84 or 83. They're set up basically the same. You will have to be careful about you would have to enter it into a matrix. If that's something that's a familiar word to you, great. If it's not, I mean, go ahead, give the instructions a try. If you can't figure it out, you know what, we're not going to do any really big ones by hand. That's just really not going to be where we're at. So our conclusion, we already gave that two-part conclusion, but this is where you kind of tie in together what you notice in the conditional distributions and the side-by-side bar plot. So we suggest we have very strong evidence there's a relationship between the type of wine purchased at the store and the type of music being played or not being played. From our side-by-side bar chart, it looks like French music had a strong influence on Italian wine purchases, and overall French was pretty popular. So we're just combining the two write-ups. That's what this is. But yeah, the purchase of other wine, it didn't seem to be as strongly influenced by type of music being played. And I'm going to assume that's local, but you know, there's tons of wine that aren't local to the U.S. So what do I know? So here's an example, just a short little one. We have the following table of counts on opinions of texting and driving. So we have, so two questions were asked. First, we hopefully randomize the order of the two questions. We asked folks if they ever text and drive. And they either said yes or no. And then we also asked the people if they think that texting while driving is dangerous. And they said yes or no. So, like here, 12 people that say they text and drive think that texting and driving is dangerous. Versus 8 of the people that text and drive said they don't think it's dangerous. And you can go ahead, go through, find these totals. So 20, that's 7. So it should be 27 both ways. Yeah. So there we go. So based on the table in the previous slide, what is the correct table of expected counts? So I can tell you right off the bat, this is the observed. You can rule that one out. Anytime you can rule out an answer without having to really go into that one, it saves you some time. Okay, so I've given you all a moment here. So looking real quick, so you're going to have to go ahead and for each of these cells, of course, these two are the same. So definitely do it for either this cell or that cell. Do the row total times the column total divided by the total total. So looking here, it's going to be table B. So last question on here, the expected count conditions are met. So this is a 2x2 table. It's very, very small. But remember, the conditions are slightly different for a 2x2 table. So looking right off the bat, remember we said, hey, are any of them, so they're all at least 1, and that's good. But we have 2 of these. 2 out of 4 cells are less than 5. This is not going to be something that's going to be okay for a 2x2 table. What it means is you took too small of samples, that your expected counts are less than 5 in this scenario. So, false. We do not meet our conditions here. We have 2 of our expected counts being less than 5. That's not okay. So that is going to be it for lesson 11. I will look forward to talking with you all on the discussion boards.